This video will provide an overview of calculating energy of a reaction for mass defect and completing our notes from class. We talked about the use of mass defect to calculate the binding energy of an atom. It can also be used to calculate the energy of a reaction. Specifically, a nuclear decay reaction, such as plutonium-239 decaying. The first step is to write a balanced equation. We are given that it emits an alpha particle. You can either abbreviate this as an alpha sign, or if you're going to use helium nucleus, you need to make sure that you include that the electrons are not part of it, that it has a +2 charge. Mass number is conserved. But we need to figure out what element goes there. So using a periodic table, we can find that plutonium is atom 294, so it has 294 protons. If it decays by alpha, it loses 2, forming uranium-92. Once we have the balanced equation, we can then use the masses to calculate the energy of the reaction. For any kind of energetic problem, we always want the mass to be the final minus initial. The final mass in this case is the mass of the uranium, 235.04393 AMU, and the alpha particle, 4.00260. So we add those together. Minus the initial, which was given in the problem. So we can plug this in our calculator. Notice that the sign is negative. That means that the final mass was less than the initial mass. And the question is, where did that energy go? Well, the energy went into stabilizing the atom or was released upon formation. We can now use this mass to calculate. Notice we are going to want to get to units of joules per mole because that is how we express reaction energies. And we can remember that 1 AMU is the same as 1 gram per mole. And this will allow us to work in the units of mass. The other thing to note is significant digits. We started with values that had 3, 5, 7, 8, and 3, 5, 6. So we started with 6 to 8 sig figs. We are down to 3. This is why you need very precise measurements to do these calculations. We can now use the famous E equals mc squared to do this next level of calculation. Notice that joules is kilograms, not grams, so we need to convert our grams to kilograms. We can now input our values into our calculator. And we get an answer, minus 5.06 times 10 to the 11th joules per mole. This is a very large amount of energy that is released